Okay, but we're going to go through a couple different models of the atom here to talk about electron configuration. So this model right here is called the Bohr model. This was discovered or hypothesized, I guess, by a guy named Niels Bohr. Okay, and his thoughts about electrons were that they circled the nucleus in very strict paths. Okay, he thought they just went in straight circles around this nucleus, and they had very, very defined paths. Okay, and he called them orbits. In his model, he said that electrons had the lowest energy state, or they had the lowest amount of energy in them when they were closer to the nucleus. So the closer to the nucleus they were, the lower energy state they were in. Okay, they had less energy. So he also said that electrons in this model couldn't be located between those two energy levels, or between those energy levels. They were kind of like rungs on a ladder, so you can't be standing in between. You have to be on one rung or the other. So that's what he hypothesized about these electrons, is that they have to be located on one orbit or another, one energy level or another. They can't be found in between. This was his hypothesis for this model. Okay, that electrons have to be located on one energy level or the other. They can't be found floating anywhere in between. Okay, our next model is called the quantum model. This one we're going to spend a little bit more time on, but this is a sketch of what the quantum model looks like. It starts with a dense region in the middle, so it's more shaded in the middle. We think electrons are closer to the middle, and as it fans out, we think electrons might be fewer and far between. So that's what that shaded circle means, is that that's our prediction area of where we think we're going to find electrons. Okay, so probability of finding an electron in the cloud surrounding the nucleus is proportional to the density of the cloud. So what this tells us is that the darker the circle is in the middle, the more likely it is that we would locate an electron in that region. Okay, and we're going to go into the quantum model a little bit more extensively than we went into the Bohr model. But the quantum model gives us a pretty good guess about where we can find an electron. Okay, it has different regions, it has different orbitals. We're going to look at where we think we can find an electron based on this quantum model. Okay, and we're going to look specifically today at something called a quantum number. Okay, the quantum number gives us specific properties of orbitals and properties of electrons within those orbitals. Okay, so each electron is given a quantum number within an atom. Okay, so within an element, each electron is given a specific quantum number. And we're going to look at how we find those quantum numbers here depending on electrons and their location. Okay, so these quantum numbers, the whole goal of the quantum number is to give us a better idea about where an electron would be located. Okay, so if you want to make an extra little note of that, that's what the quantum number does. It tries to give us a little bit more of an idea about where we might be able to locate an electron. All right, so within a quantum number, there's broken up into 4 sections. So we only technically have one quantum number, but it's got 4 parts to it. So each atom and each electron has 4 parts to its quantum number. They describe 4 different things. They describe the main energy level, the shape of the orbital, the orientation of the orbital, and the spin of an electron. Okay, so each quantum number has 4 parts to it. And we're going to go into each of these 4 parts a little bit more exclusively. I wanted to just introduce it first. So this is going to describe the 4 parts, and we're going to look at each of those 4 parts individually. Okay, but each quantum number has 4 basically numbers that go into it. Okay, and what this principal quantum number does is it describes to us its energy level, okay? We symbolize it by a lowercase n. Okay, so each quantum number will be given with 4 different parts to it, and the principal quantum number is signified by a lowercase n. So what this principal quantum number tells us is it tells us the main energy level of the electron. It basically tells us how far away from the nucleus that electron is. Okay, what level is it at? How far away from the nucleus are we? Okay, all of our first quantum numbers, or all of our principal quantum numbers, are positive integers. They begin with 1. They go up to 7 or 8. Okay? Positive integers. So we don't have any principal quantum number that's equal to 0. We're all 1 or above. Okay, if we have a principal quantum number, or if we have a first quantum number that says n equals 1, that means we're at the lowest energy level. Our electron that we're looking at is at its absolute lowest energy level. It's in the space closest to the nucleus. That's what n equals 1 tells us, is that this electron is located in this energy level that's closest to the nucleus. Okay, so what would n equals 2 tells us? What would that tell us? Yeah.
It's in the second closest place to the nucleus.
Yeah, it's a level out, right? It's an energy level farther from the nucleus. So it's located at a distance farther from the nucleus. Okay? If we've got one electron at n equals 1, if we've got one electron at the lowest energy level, we can have another electron there as well. So more than one electron can occupy that lowest energy level. Or more than one electron for a single atom can have the same principal quantum number. Okay, we can have 2 electrons at that lowest energy level. So if you see 2 electrons that have the same principal quantum number, it's okay. The first number that comes in our overall quantum number, which has 4 parts, that first number tells us how far away from the nucleus our electron is located. Okay? The lower the number, the lower the principal quantum number, the closer it is to the nucleus. Does that make sense? Okay. All right, let's look at our second quantum number now. Do we have any, and it's called the angular momentum quantum number. Okay, like we talked about, each quantum number has 4 parts. This is the second of the 4 parts. Okay, it's called the angular momentum quantum number. Lowercase n. This quantum number is symbolized by a lowercase l. Okay, it's a lowercase l. It's not a 1. It's not an I. That's a lowercase l. Okay, so you might see me write it in cursive so you can kind of tell that it's an L. Hopefully. Okay, but it's a lowercase l. So in our quantum numbers, we have n and we have l so far. Right? N is our principal quantum number. It tells us how far away from the nucleus our energy level is, or our electron is. And our angular quantum momentum number is symbolized by an L, and this tells us the shape of our orbital. Okay, it tells us the shape. So go ahead and get that written down, and then I want to explain to you what an orbital is. Okay, so an orbital is kind of the pocket or the like sac or whatever you want to call it that holds electrons, that houses electrons. So orbitals are pockets of space that contain electrons. And different types of orbitals have different shapes, depending on their location around the nucleus, depending on how they fit together. Orbitals kind of fit together like a puzzle. So the more orbitals we have to have, meaning the more electrons we have to have, they have to fit together differently. So they have different shapes. Depending on the energy level, depending on how far away they are from the nucleus, all that kind of things depends on the shape and the size of those orbitals. Okay, so when we talk about orbitals, I want you to think about little pockets that hold those electrons, that contain those electrons. Okay, does that make sense? So this second quantum number tells us the shape of our orbital. Okay, and we're going to go through 4 different shapes. But the number of shapes that we have is only possible to be equal to n. So what does n stand for? Our first quantum number, right? Our principal quantum number, our first energy level. So if I only have n equal to 1, if I'm only at the first energy level, that means I only have one type of orbital shape, right? Because I only have one type of orbital. Okay, so the number of orbital shapes possible is equal to n. So if I have a quantum number, or if I have an electron that has a principal quantum number or an n equal to 4, how many different orbital shapes could I have? 4. I could have 4. Okay, so let's walk through these just a little bit. When we look at the value of what L would be, the value of our angular quantum number, they can be 0 and positive integers less than n equal to n minus 1. So they can be 0 to 1 to 2 to 3 to 4 to 5, whatever. Okay, so they start at 0 and they go all the way up to n minus 1. And we're going to do some examples of this, so just try to think through what we're talking about here, and then we'll look at some examples. Okay, so if I have a principal quantum number of 4, I have n equals 4, that means how many different orbital shapes am I going to have? 4, right? And the numbers that correspond with that, the values for L that could correspond with that would be 0, 1, 2, and 3. I would have an L equal to 0, 1, 2, or 3. Right? I have 4 options. They start at 0 and they go all the way up to n minus 1. So since n equals 4, I'd have an L that's equal to 0, 1, 2, or 3. Does that make sense? So what if I had an n equals 2, my L value would be 1 or 0. Okay, if I have n equals 2, I'd have 0 or 1 as my L values. I know this seems a little bit abstract right now. I know it seems a little bit out of place. We're going to put it all together here in just a second. Okay, so if I had n equals 4, my L value would equal 0, 1, 2, or 3. Okay, that means I could locate an electron in either of those 4 types of orbitals. Okay, and then the rest of the quantum numbers are going to give me even more information about that electron. Okay, but if I have an n equals 4, that means my electron is located in that 4th energy level, and it could be either in the first shape of orbital, the second shape of orbital, the third shape, or the 4th shape. Okay? Are we kind of getting it?
Yeah.
I know it. Okay? If L equals 0, it's got a certain shape that orbital is going to be in. If L equals 1, I'm going to have a certain shape that orbital is in. Okay? So our L values have letters and shapes that correspond with them. Okay? So now we're going to know how far away from the nucleus our electron is and what shape of the orbital it's going to be in. Okay? In the left-hand column are our L values. That means if L is equal to 0, we call it an S orbital. If L is equal to 1, we call it a P orbital. If L is equal to 2, we call it a D orbital. If L is equal to 3, we call it an F orbital. All right, so I want you to get this table written down, and I also want you to go ahead and draw the shapes of these orbitals underneath there. Okay, so what this tells us is that if we've got an n value equal to 1, okay, if we've got an n value equal to 1, what would my L value be equal to? 0, good. So what would the letter that corresponds with this be? S. And what would the shape of my orbital be? This circle right here. So that tells me that I've got an electron on the first energy level in this S-shaped orbital. So it's in that kind of sphere right around the nucleus. It's as close as it could be, which is exactly what this first energy level tells us, right? It's as close to the nucleus as it can be of our orbital shapes. And I just want you to kind of look at these right now. You don't have to go into drawing these or anything, but our S orbital a little bit more closely here. Our nucleus is always located directly in the middle of our orbitals, okay? So our S orbital is any of this space surrounding it right in this sphere, an electron could be located in that sphere, okay? Okay, so when we have n equals 1, we know that L can only be equal to 0, which corresponds to an S shape. which is a sphere. Okay, so that one s orbital will contain that electron. For n equals 2, we've got two different sublevels we could be at. So what are our L values for n equals 2? If n equals 2, L has to equal what? 0 or 1, which corresponds with both s and p orbitals. S and p orbitals. Okay, so for these, we would call them 2s orbital and 2p orbital. Okay, they're in energy level 2. They're in the second level away from the nucleus, and they can have both an s orbital and a p orbital. Okay, so that electron is located in the second energy level in either an s orbital or a p orbital. Okay, and I promise once we put this all on the periodic table, it's going to make even more sense. Okay, for n equals 3, we've got 3 sublevels, S, P, and D. So for n equals 3, our L values are equal to 0, 1, and 2. And those numbers for L correspond to an S, P, and a D orbital. Right? Isn't that what your chart tells you? Okay, so for these, we would call them 3s, 3p, 3d. Okay, you have each of those 3 types of orbitals. Okay, so as we move down the periodic table, you can start to see what those orbitals, you have more electrons as you move down energy levels, because you're increasing the number of protons, which increases the number of electrons. So you're going to have more and more types of orbitals to hold those electrons. Okay. All right, we're going to look at our third part of our quantum number here really quickly, and then we're going to kind of put it all together after we talk about 3 and 4. Okay, so our third is called our magnetic quantum number. Our magnetic quantum number. Okay, and it's symbolized by an M, a lowercase m. So when we talk about orientation around the nucleus, we're talking about, is it sitting on the x-axis, is it sitting on the y-axis, on the z-axis? Where is it located around the nucleus? Okay, that's what this magnetic quantum number tells us. So magnetic quantum numbers, or M, can be values -1, 0, or +1. -1, 0, or +1. Okay? Whole numbers from negative L. I'm sorry, I read that wrong. Negative L to positive L. Okay, so that means that if L was 3, right, we would have -3, -2, -1, 0, 1, 2, and 3. So we have all those options. That's my fault. Negative L to positive L. It depends on the number of orbitals and their shape. That's where it comes into kind of fitting like a puzzle. Those orbitals have to be able to stand to be around each other, kind of. They have to fit together in the right orientation, otherwise it won't work. So that magnetic quantum number gives us a better idea of how they fit together, where their shape is, where they're located, all that kind of stuff, depending on the nucleus. Okay, so I want you to take out page 108 and 109 in your book to read just a little bit more about magnetic quantum numbers. Our last is called the spin quantum number. And it has only 2 possible values, either +1/2 or -1/2. Okay, it only has 2 possible values, +1/2 or -1/2. And what it tells us is the fundamental spin state of an orbital. So orbitals, when they are electrons, when they're paired together, have to have opposite spins. Okay, they have to be spinning in opposite directions in order for them to be paired. And so this spin quantum number tells us which direction each of those electrons are spinning. Okay, +1/2 or -1/2. No. Nope, it's just going to be the positive 1/2 or the negative 1/2. Okay, a single orbital, so all these orbitals we've been talking about, a single orbital can only hold 2 electrons. And when 2 electrons are located in an orbital, they have to have opposite spins. So if one of our electrons has a positive 1/2 spin, the other electron in that orbital has to have a negative 1/2 spin. Okay, so each single orbital, a 1s orbital or a 2p orbital, whatever, those can only hold 2 electrons. Okay? And within that, you've got to have opposite spins. So all these pairings that we've talked about, the 1s orbital, 2s orbital, 2p orbital, those are different shapes located in different spots around the nucleus, and they can hold 2 electrons. So we're going to be able to look at each individual element and look at its electron configuration, where those electrons would be located based on the shapes and sizes of those orbitals. Okay. So now I want your periodic table out, if you don't have that out yet. Okay, I know I just told you to get it out. Shaded depending on the shapes of their orbitals. Okay, these first 2 groups, groups 1 and 2, are what we call the S block elements. Okay, so these elements right here are S block. Okay, those outer shell electrons are in the S orbital. So these first 2 groups right here, groups 1 and 2, you can write an S above those, or if you want to shade them or whatever you want to do, I wouldn't probably shade them too much, but these are the S block right here, these groups 1 and 2. Then I want you to jump over to our groups 3 through 8, and these are called the P block. So all 6 of these groups, 3 through 8, are called the P block. Okay, so these groups are S, these groups are P. This transition metals right here in the middle are called the D block. And the lanthanides and the actinides are the F. Okay, and where do these letters look familiar from?
The same thing that are our orbitals.
Yeah, those are our orbital shapes. Okay, so we're going to start putting this together on the periodic table and looking at our electron configuration of individual elements, okay, based on their location in the periodic table. Something that I also want you to look at is that as you go down the periodic table, period 1, period 2, period 3, these values right here are going to be equal to your N values. Okay, so if I'm in period 1, that means N equals 1. If I'm in period 2, N equals 2. If I'm in period 3, N equals 3. Right? As I move down the periodic table, I gain another shell of electrons. I gain another group, another level, another energy level. Okay, so as I move down the periodic table, I'm going to gain an energy level all the way down to the bottom. Okay, so whatever period it's in, whatever row on the periodic table, that's going to be equal to its N value. These are our orbitals right here. These are our orbital numbers and our orbital shapes. So when electrons fill these orbitals, it's in their nature to fill the lowest energy levels first. We're not going to have an electron that fills a 3p orbital before it fills a 1s orbital, right? It's going to fill the lowest energy level first, and then it's going to go out. Okay, so our lowest energy level orbitals are the 1s orbitals. Okay, and then the 2s orbitals, and then the 2p orbitals. Okay, so those electrons are going to fill all those orbitals as it works its way outward. Okay, so if I've got an element that's got 30 electrons, it's going to fill 2 in this orbital first, then 2 in this orbital, then 2 in this orbital, 2 in this orbital. It's going to fill every single orbital first before it starts to fill that outer shell. Okay? So it's always going to go to its lowest possible energy level, or its lowest orbital, its closest orbital to the nucleus first. Okay, so I want to take a look back at this periodic table for just a second. So I'll come back to this slide. Okay, each of these 1s that indicates a type of an orbital, right? Do we understand that? The 1 tells us the energy level, the S tells us the shape of the orbital. So a 1s is a type of orbital, right? It's in the first energy level and it's a sphere. 2s is another sphere, okay? It's in the next energy level. So it's in the second energy level and it's the same shape, it's a sphere, right? Because that's what S corresponds with. Then we go over and we fill the 2p orbitals. And the 2p orbitals, what shape was the p orbitals? What did they look like? Kind of like a dumbbell, right? Look like a dumbbell. So after we fill the 1s orbitals and we fill the 2s orbitals, we're going to go fill the 2p orbitals. That's where electrons start filling next, okay? So you can see we follow along on the periodic table. We're going to fill those electrons first, okay? You fill the lowest energy level first. So we'll fill the 1s orbitals, then we'll fill the 2s, then the 2p, then 3s, then 3p, 4s. Then they kind of, the d orbitals shift around here a little bit into 3d, blah, blah, blah. Okay, but that's going to be the order that we'll fill things in. And I'll give you a handout to help you with the order in which you fill things. Okay, but do we understand that electrons will fill to the lowest energy level first? Okay. So this rule and the fact that they fill their lowest energy level first is what we call ground state electron configurations. We're looking at an element at its most basic, at its most stable state. We're looking at its ground state electron configuration. So not when it has a charge, not when something crazy is going on. We're looking at an element in its very most ground state. Okay, it's stable, it's calm, nothing crazy is happening. We're looking at these ground state and where we would find an electron in its ground state. Okay, when something is at its most stable time. Okay, so we are going to now be able to determine the ground state electron configuration for each and every atom. We're going to tell what orbitals it has, how many different types of orbital it has, where our electrons in the outermost shell are located, all that kind of stuff. That's what our electron configuration is going to tell us. Energy level first. So this stuff to the side tells us that we're going to start at the bottom. We're going to fill our 1s orbital first. Then we're going to fill our 2s orbital. Then we fill our 2p orbitals, our 3s, our 3p. This is the order that we fill our orbitals in, all the way up until we get to our topmost outer energy level electrons. Okay? And this is called the Aufbau principle. So telling us that we fill our lowest, most energy level first is what we call the Aufbau principle. Okay? So down here you see low energy at the bottom is our 1s orbitals. And then as we get higher or we get lower on the periodic table, really, we start to have higher and higher energy orbitals. Okay, those electrons contain more and more energy. They're farther from the nucleus. They want to kind of get released or easier. They're easier to get released because they're farther from the nucleus. Okay. The lower the principal quantum number, the lower the energy. So anytime we have n equals 1, we've got low energy. N equals 2, right? We've got pretty low energy. When we get up to n equals 7, we've got pretty high energy electrons. Okay? Within a single energy level, so within n, within our period on the periodic table, S is always going to be the orbital that fills first, then P, then D, then F. Okay? So within a certain energy level, we always fill our S orbitals first, then we fill our P orbitals, then our D orbitals, then our F orbitals. So we would never have a 2F orbital filled before we have a 2S orbital. Right? We've got to fill that lowest energy level first. And I know a 2F orbital is not even a real thing, but I want you to understand we fill it in that order. Okay? And in.
1.
Okay, so let's look at hydrogen right now. Its electron configuration is 1s1. Okay, so hydrogen's in the first energy level. That's what this number right here tells us. That's N. This tells us that it only has an electron contained in the s orbital, because that's as far as its electron configuration goes. It has one electron located in that s orbital, because it only has one electron total, right? So it's got one electron, and it's located in the 1s orbital. That's what this electron configuration tells us. Okay, so let's look at helium. 1s2. 1s2. How many electrons does helium have? 2 total, right? And they're both located in the 1s orbital. Okay, because it's in energy level 1, and that helium is considered still in the s block, even though it's listed in group 8. Okay, so be careful about that one.
So all these atoms are neutrally charged?
Yes. They're all in their ground state. So when we looked at our p block, I want you to make sure and make a note that helium really is an s block element. It's not a p block element. Okay, even though it sits on that side of the periodic table, helium is still an s block element because it's only in energy level 1, which means it can only have L equal to 0, which is an s-type orbital. Okay. Let's take a look now at boron. Boron says it is 1s2 2s2 2p1. Okay, so let's count how many total electrons boron has. How many does it have based on the periodic table? How many does boron have? 5, because its atomic number is 5. It's a neutrally charged atom. It's got 5 total electrons. It's got 2 electrons in the 1s orbitals, 2 electrons in the 2s orbitals. It goes down an energy level. Then it's got 1 electron in the 2p orbital.
Oh, so the 2x stands for...
Yep, so if you look at your periodic table and you follow along, you can see us fill the 1s orbitals, it fills the 2s orbitals, and it's in the first section of the 2p orbitals. Okay, so if you look on your periodic table, I'm not going to pull the periodic table up here. Right, is it kind of coming together? So if you look at boron, we filled the 1s orbitals, which is hydrogen and helium. We filled the 2p orbitals, which is lithium and beryllium. We move over to 2p, and we have 1 electron in that 2p orbital. So those blocks on the periodic table help us with our electron configurations.
So when we get down to the bottom, it's going to be a big...
It's going to be much bigger. And look at our pathway that I handed out to you. We filled the 1s orbitals first, then we filled the 2s orbitals, then we filled the 2p orbitals. We've only got 1 electron in that 2p orbital. That's why we give it a 1. And if you add up your total electrons, if you add up this number plus this number plus this number, it should give you your total number of electrons that that element has that you're trying to represent. Okay? You will have to know the order it goes in, but you should be able to know it based on the periodic table. So that's just kind of a helper for right now. But you should be able to know based on the periodic table. So we went across the periodic table first, then you move down. Then you go across, then you move down. Okay? Does that make sense? All right, let's take a look at a little bit bigger one. Let's look at neon right here. Okay, so neon tells us 1s2, 2s2, 2p6. So why can the p orbital hold 6 electrons?
Because it's the p block.
It's the p block. There's 3 different types of those orbitals, and so total, the p orbital can hold 6. Okay, if we really wanted to get really specific, we would say px2, py2, pz2, but we're not going to get that specific into it. Okay, we're going to tell the overall p orbital configuration. Okay, so neon has how many total electrons? 10. 10. Does these numbers add up to 10? 1, 2, 2, and 6?
Yes.
Yes, that means you're on the right track. So for neon, we just filled the s orbitals, the 1s orbitals. We're in period 1. These are s orbitals. We filled 2s2. That's these 2 right here. We filled 2p, 1, 2, 3, 4, 5, 6. Okay? So this tells us for neon, we've got 3 different types of orbitals. We've got a 1s orbital, we've got a 2s orbital, and we've got 2p orbitals. Okay?
So if it was fluorine, would it be 2p5?
Exactly. If it was fluorine, we go 2p5. If it was oxygen, we go 2p4. Yep? Okay? So let's try some with the 3rd energy level. Let's try the electron configuration for sulfur. Electron configuration for sulfur.
What's the highest amount that can go into 2p?
6. Only holds 6.
And then after that,
So what is it?
3s.
Then you move down. Yep, 3s. Okay, do we agree with our electron configuration for sulfur here?
Yes.
So sulfur has 1s orbitals that are full. It has 2s orbitals that are full. It has 3s orbitals that are full. I'm sorry, 2p orbitals that are full, 3s orbitals that are full, and 3p orbitals that are not quite full. Right? The 3p orbitals are not completely full. It can hold 6. It only has 4. Okay? How many total electrons should sulfur have? It should have 16. So do these numbers right here add up to 16?
Yes.
Okay, we need to make sure that those are superscripts. Don't put those below. Don't put them down here. That's not where they go. They go up top. Okay?
1s2, 2s2, 2p6, 3s2.
Do we agree?
Yes.
Yeah. Very good. Any questions? Did we add up our electrons? 2, 4, 10, 12. Magnesium has an atomic number of 12, which means it should have 12 electrons. Okay, which is what we have accounted for here. So we've got full, all of these orbitals that we have are full, right? Because we ended with 3s. Our 3s orbital has 2 electrons in it, which means we've got full orbitals all around. Okay? Let's try the next 3. I want you to try those on your own. Potassium here.
Okay, 1s2, 2s2, 2p6, 3s2, 3p6, and 4s1.
Okay. Do we agree?
Yes.
Yeah, that looks fine with me. It should end up with 4s1. We've got all of our 3's filled, and we've got our 4s1. Good, yeah.
So we have to have the
S2, 2s2, 2p6, 3s2, and 3p2.
3p2. Looks good with me. Okay, so if I would give you an electron configuration, let's say that I give you this electron configuration. Can you find the element? Can you find the element that I am describing?
Oh, what's that last one?
It's a 5, 3p5. So how can you determine what element that is? Grace, tell me.
add up the superscript.
Yeah, you can add up all the superscripts. That's going to tell you the number of electrons. Okay, that's a good idea. So this one has how many electrons? 17, which means it has to be with atomic number 17, which is chlorine. Good. What's another way we could determine what element it is? Go through all the blocks. You count. So I go, okay, I've got 1s orbitals. Those are full, so it's not either of those. I filled my 2s. I filled my 2p. I filled my 3s. And I'm in 3p5. So here's my 3p block right here. I'm in period 3. I'm in the p block. So I go 3p1, 3p2, 3p3, 3p4, 3p5. And end at chlorine. Okay? You can do it either way. Okay, so you really are only looking at the last portion of that. The very last section. Assuming that everything else was done correctly up to that point, you can really only look at the last couple of those to see what your final orbitals are. Okay? So that's what we're going to look at next, is how we can abbreviate these electron configurations a little bit more. Okay, so we have a way to kind of shorten them down and condense them a little bit. Okay, so we can abbreviate these by using the noble gases. What group are the noble gases in? Group 8 or 18, right? They're all the way to the right. So that's helium, neon, argon, krypton, xenon, and radon. Okay, those are the noble gases. So we can abbreviate these electron configurations by using the noble gases to our advantage. All right, so I want you to find the normal electron configuration of calcium. I want you to tell me the normal electron configuration of calcium. We just did it. Right, is this our electron configuration for calcium? We end up with 4s2. Okay. So what's the noble gas in the energy level or the period just above calcium? Argon, right? Calcium is in period 4. So the noble gas in period 3 is argon. Okay? So here's how we can abbreviate calcium's electron configuration. We're going to say its configuration is exactly like argon plus 4s2. So it looks like this. Noble gas, and then we just start from there, 4s2. So after that noble gas, we pick up at our next spot. So we go to energy level 4, so we know we have to fill 4s, and then we can go from there. Okay? So if you end up looking at your pathway and you want to know where it starts on your pathway, you've got to know that argon is level 3, okay, or N equals 3, it's period 3. So we know calcium's in level 4. We have to fill the 4s orbitals first. So you can start with 4s, and then you can just pick up on your pathway from there. Okay? You can only use this rule with noble gases. You cannot put potassium here. Okay? It only works with noble gases. So you cannot use any element you want. It's only the noble gases. Okay? Mm-hmm.
Do that on